Welcome to the Computer Security Seminar from Purdue University. I'm Professor Wagstaff, and I'm running the seminar, and I am going to speak again this week. I would like to find some other speakers, so if any of you out in the audience there would like to give a talk, by all means contact me, and we will set up a time for you to talk. Today's talk is about cryptanalysis of Diffie-Hellman and Pohlig-Hellman. These are two rather different kinds of cryptographic tools. And I'm going to tell how each one works, and then tell a little bit about how one would break them. It turns out that you have to solve exactly the same problem to break both of them. Okay, so we'll begin with Euler's theorem. Both of these cryptographic tools use Euler's theorem, and in fact they use it in a very simple case. Basically, we just need the special case of Euler's theorem when m is a prime number, and in that case it is called Fermat's theorem. Okay, so we'll let m be a prime number and a be some number relatively prime to m. That's the same thing as saying that m does not divide a if m is prime. Okay, then the Euler phi function is the number of numbers between 1 and m which are relatively prime to m. In case m is prime, phi of m is just p minus 1. Okay. So in the case that we are interested in, Euler's theorem says that a to the power p minus 1 is congruent to 1 modulo m. What this means is that if you raise a to the power p minus 1 and you subtract 1, you get a whole number, a multiple of m. There are special techniques that one can use to raise numbers to very large powers. For example, if the exponent p minus 1 is a 100-digit number, and m is a 100-digit number, and a is a 100-digit number, you can raise a to the power p minus 1 modulo m in a very short time, maybe a few milliseconds. Okay. We're not going to worry about the proof of this at this time. Okay, so we're going to talk about one cipher, which is an example of an exponentiation cipher. Exponentiation just means that you raise something to a large power to encipher, and you also raise something to a large power to decipher. So first of all, where do these numbers come from? We're going to choose a positive integer n, probably a large positive integer n. Think of n as having 100 or 200 decimal digits. And we're first of all going to encode or represent our plain text in blocks of size that can be represented as numbers modulo n. This means they have to be in the range 0 through n minus 1. So, for example, you could take the ASCII code representations of the alphabet and just concatenate the ASCII codes until you get a block size which is as large as possible, but less than n. Okay, now, so all we have to do is encipher and decipher numbers. When they are deciphered, that is, when you have a plain text, you can go back to the letters by breaking it up into smaller numbers, each of which represents an ASCII code. For example, they might be 8 bits long, or maybe 7 bits long. But when we put a lot of them together, we have a large number m, and we have to encipher m. We're going to encipher all of these letters, which are represented in m, all at once, and we do this by raising m to a power, let's say the e power modulo n. You can do this fairly easily. You decipher it, the ciphertext, by raising the ciphertext to a power d. If these two exponents, e and d, are chosen properly, when you encipher c and then decipher it, you will get back. Sorry, when you encipher m and decipher it, you will get back to m for any m in this range, and e and d have to have the property that e times d is congruent to 1 modulo phi of n. So if n is a prime number, this is just n minus 1. Okay, so the reason this works is because of Euler's theorem. Euler's theorem is what makes the algorithm work. If you write, ed congruent to 1 modulo phi of n means that ed is one more. Ed minus 1 is a multiple of phi of n. Let's say it is t times it, and then when you raise m to the e power and you raise that to the d power, you get m to the power e times d modulo n, and you can write ed in this way, and the m to the power phi of n is congruent to 1 by Euler's theorem, and so therefore that part of it goes away, and you just have m to the power 1, which is what you want. Okay, you can build a lot of different ciphers based on this. One of them is the RSA public key system. In that cipher, the modulus n is the product of two large prime numbers, p times q. However, we aren't going to talk about that today. Instead, we're going to talk about the Pohlig-Hellman cipher. Pohlig-Hellman is not a public key cipher. You don't make anything public normally. You let n equal p be a prime number, then phi of p is just p minus 1, and the requirement on e and d is that e times d should be congruent to 1 modulo p minus 1. This means that d is a multiplicative inverse of e modulo p minus 1. Okay, there are two basic ways that you can use the Pohlig-Hellman cipher. In one method, you keep all of the numbers p, e, and d secret. All three of these numbers together form the key. If you want to encipher your own personal files, you can do this. You can use this method. You should keep the p, e, and d all of them secret. Or if two people want to communicate secretly, they have to agree on P, E, and D. Say one of them knows it and he writes it down on a piece of paper and tells the other one, and the other one reads the piece of paper and then destroys it and memorizes them. Then they can communicate. The first person enciphers a message M by raising it to the E power modulo N, sends the ciphertext to the other person, and the other person deciphers it by raising C to the power D modulo N, and this recovers M. Okay, so the other method of using the Pohlig-Hellman cipher is this. P can be public, or at least you don't worry if people know what P is. And E and D should be kept secret. The key is simply the pair of two large numbers, ED. Each user has their own secret key. Each pair of users who want to communicate have to choose a key pair, ED. Method 2 is actually more popular than method 1 because it often takes a fairly long time to find a good large prime. You want to have a large prime number, say 200 decimal digits or so, and it may take you a few minutes to generate one. So you just find one in a public website, and then you choose your own secret E, and you calculate D from it. There is an algorithm called the extended Euclidean algorithm, which lets you calculate D from E and P. So also method 2 has some interesting mathematical properties that we will see in just a moment. You can build a public key system called the Massey-Omura system from method 2. It's just a variation of method 2, but I'm not going to talk about that today. You can also play mental poker using another variation of method 2, and I will talk about that today. So let's look at the cryptanalysis of the Pohlig-Hellman method. Suppose there is a known plaintext attack. What that means is that the enemy knows the plaintext and knows the corresponding ciphertext and wants to figure out what the key is so that they can decipher more messages, ones for which they only know C and not M. So let's say that so this is actually giving the cryptanalyst quite a bit. So let's say the cryptanalyst knows the prime modulus P, and knows the plaintext M, and also knows the ciphertext C. Then all the cryptanalyst has to do is find the exponent E, so that C is congruent to M to the power E modulo P, or equivalently find the exponent D so that M is congruent to C to the power D modulo P. Either one of those would do. If you can find either E or D, you can find the other one very easily. Now it turns out that this is a well-known problem in number theory. It's called the discrete logarithm problem. You are given positive integers a, b, and m, and you have to find a number x so that a to the power x is congruent to b modulo m. Okay, in general, when A, B, and M are 200-digit numbers, this is well known to be a hard problem. There's a few easy cases. For example, when the modulus is a prime, as it is in the Pohlig-Hellman method that we just talked about, and p minus 1 has only small prime factors. That means that every prime factor of p minus 1 is a relatively small number, like less than 10 to the 10th or so, something like that. There are a few 200-digit prime numbers p, so that all of the prime factors of p minus 1 are less than about 10 digits, but only a few of them. If you somehow choose a random prime p, then it's unlikely that p minus 1 would have this nice property, and in any case, you could determine whether p minus 1 had only small prime factors very easily. Okay, but in the general case, this problem is of the discrete logarithm problem is about as hard to solve as it is to factor a hard number about as large as the modulus m. Okay, so that is the discrete logarithm problem, and I'll say more about that in a few slides. Okay, let me tell you a variation of the Pohlig-Hellman method where you can use it to play mental poker. Now, it's not quite mental poker because you have to do calculations with large numbers. In particular, the players have to raise 200-digit numbers to large powers, which are like 200 digits. But anyhow, if you have a computer, this is really quite easy. It just takes a few milliseconds of computer time to do these calculations. Although a human being would not likely do the calculations mentally, but still, it's called mental poker. You can think of doing poker by email. So you've got several players all connected by email, and they want to play poker. So one player could be the dealer, and he could deal all of the hands, and then send the hands to the other players, and then they would all bet. And well, as you can probably guess, the player who does the dealing has a great advantage. Okay. Well, with the mental poker protocol, it becomes a fair game. Well, not quite, but almost. Okay, so in the game of poker, you play with a deck of 52 cards. Each player is dealt 5 of the 52 cards. Each player can see his hand, but not the other player's hands. Players make bets, probably for money, based on their hands. There is a ranking of all of the possible 5-card hands, and the best hand wins. In some of the variations, some of the cards are revealed and some are not. And in some other variations, some cards can be replaced by cards not yet dealt. Okay, so the mental poker protocol for poker requires a fair deal. The players can see their own hands, but they cannot see other hands. the dealer is one of the players. The hands have to be disjoint. You can't have everybody just choose 5 out of the 52 cards, because some of them might choose common cards. And you want all of the 52 choose 5 possible hands to be equally likely. You also want to have the possibility of a player replacing cards, and you also want to have the possibility of players revealing individual cards one at a time without revealing the other cards. And at the end of the game, all of the players should be able to check all of the calculations which they have seen through mail messages to each other and verify that nobody cheated. Okay, so I'm going to tell you how to do this, how to do all of this using a variation of the Pohlig-Hellman cipher that I just talked about. We're going to assume that there are just 2 players, Alice and Bob. There are also similar protocols for 3 or more players. It just makes it slightly more complicated. So the players all together they choose a large prime. It doesn't have to be secret or anything. Everybody knows it. Maybe other people know it too. Each player secretly chooses a pair of keys that could be used for method 2 of the Pohlig-Hellman system, just for that one player. Okay, so for example, Alice would choose EA and DA, Bob would choose EB and DB. Okay, and then we define enciphering and deciphering algorithms, E sub A, E sub B, D sub A, D sub B, which mean you raise the argument to the corresponding power. So, for example, E sub A of M is M raised to the E sub A power modulo P, just like in the Pohlig-Hellman system. Likewise, you have D sub A of C is C raised to the D sub A power modulo P. E sub B of M is M raised to the power E sub B modulo P. Okay, now these functions commute with each other. That means that if you have one value, say M modulo P, and you first encipher it using E sub B, and then you encipher it using E sub A, you get the same result as if you enciphered it with E sub A first, and then with E sub B second. Okay, so these they have these nice properties. You can, if you have 2 of these four functions applied to one quantity, you can. It doesn't matter what order you do these in. You get the same answer. So now let's let M1 up to M52 be 52 numbers which represent the deck. If you have a joker, well, you'll have 1 or 2 more cards. That's all right too. Okay, so at the beginning of the protocol, Bob. Let's see. Bob is going to shuffle the deck, and then Alice is going to deal. So Bob enciphers the cards as CI equals EB of MI. Recall that Bob can do EB. Bob can also do DB, but Bob can't do EA or DA. Only Alice can do those 2 functions. So Bob enciphers the 52 cards, producing 52 numbers modulo P, C1, C2 up to C52. Bob then sorts them in numerical order. This is a nice way of shuffling the deck. Just sort the ciphertext, and sends the shuffled deck to Alice. Alice, if she likes, can sort the cards, can shuffle the ciphertext more. Alice, of course, doesn't know what card any of these CIs represent. Alice only sees 52 large numbers. Okay? So Alice chooses five of the cards at random out of the 52. She can do it any way she wants, as long as any set of 5 cards out of the 52 would be just as likely to be chosen as any other set of 5 cards. She then sends the ciphertext to Bob, who decrypts them. Those are his hands. Okay, now Alice chooses 5 more random cards. Let's say C1, C2 up to C5. This is going to be her hand, but her hand is enciphered with Bob's Pohlig-Hellman cipher. Okay, Alice enciphers these ciphertext cards once more. She ciphers each of the 5 ciphertext cards by using her cipher EA of CI. So Alice calculates CI prime for I equals 1 through 5. This is her hand, and it has been enciphered twice. Once with Bob's cipher, once with Alice's cipher. Okay, Bob deciphers the CI primes. Okay, these are still enciphered with EA even after Bob applies DB to them to undo EB. This is where we use the fact that it doesn't matter what order you do these in. When Bob applies EA, of course, they have already been enciphered as EB of EA. So, sorry, let's try this again. They were first enciphered with EB, that's on the inside. Then they were enciphered with EA. Now Bob applies DB, but DB and EA commute with each other. You can reverse the order. So you get EA of DB of EB of MI. And the DB undoes the EB. Okay, and so then, so now they are still enciphered, but only with Alice's cipher EA. So then Alice Bob sends these 5 numbers back to Alice. Alice then deciphers them. They are just EA of some card, so Alice applies DA to them to decipher them and get back to a card. Okay, so Alice uses them as her hand. The 2 players bet, and they play poker. At the end of the hand, Alice and Bob exchange their keys, the EA, EB, DA, DB. And since they can know all of the numbers that went back and forth, they can verify things. They can make sure that nobody cheated. It turns out there is a way you can cheat, but never mind. Anyhow, this is a really neat protocol. It's a way of playing poker by mail. Okay, now here is yet another. Well, this is another problem, which also depends on the discrete logarithm problem being hard. In this protocol, 2 users want to choose a common secret key for a one key, the symmetric cipher, like DES or Rindale, and they want to do this while they are communicating over an insecure channel. There are people listening to them, eavesdroppers. The eavesdroppers have the same kind of computer that Alice and Bob have. So now Alice and Bob want to communicate using DES. Okay, but they have to choose a common key. Alice can't just say, "Hey, why don't we use this key," and send the key over the network, and then Bob say, "Okay, let's use it," because the eavesdropper will hear what the key is, and will be able to decipher their communications. So here's how they can choose a common key in such a way that eavesdroppers who have the same computing power can't find out what it is. Okay, so Alice and Bob agree on a common large prime P, and also a constant value A. A and P are publicly known. Everybody can use them. It doesn't matter. If you choose say a 200-digit prime, and you choose a random number A, that will probably be good enough. There is a tiny problem that would happen if the order of A in the multiplicative group modulo P is very small, but that's very unlikely to happen. Okay. Also, Alice chooses a secret random number A between 1 and, let's say, P minus 2, and calculates and raises A to that power, A to the power X sub A modulo P. Call that number Y sub A. Bob does the same sort of thing. Bob chooses a random number X sub B in the same range, and raises A to that power, call that number Y sub B. Okay, Alice sends YA to Bob, Bob sends YB to Alice. The eavesdropper, who knows both P and A, and sees YA and YB, can't calculate XA or XB from this unless he can solve the discrete logarithm problem. That is, the eavesdropper, let's say, would know Y sub B, A, and P, and would have to calculate X sub B. Well, unless the eavesdropper can solve the discrete logarithm problem quickly, this is hard. Okay, so having done that, Alice computes Ka, which is YB, this is the number that she received from Bob, and she raises it to the power XA. Likewise, Bob computes a number K sub B, which is YA. YA is the number that Bob received from Alice. And this is called K, and raises that to the power XB. Okay, now let's just look back at where these numbers came from. Oh, I guess this fits. Yeah, like for example, YB was A to the power XB. So now down here, when Alice receives YB from Bob, Alice raises YB to the power XA. So what is this in terms of A? Well, it's A raised to the power XB and then raised to the power XA. So this is the same as A raised to the power XB times XA. And likewise, KB is A raised to the power XA and raised to the power XB, which is A raised to the power XA times XB. This means that both Ka and Kb are congruent to a raised to the power xa times xb. If everything is reduced modulo p so that you get two numbers in the range between 0 and p, these two numbers, Ka and Kb, have to be the same number. This is because they are congruent to each other modulo p. In other words, p divides the difference between them. But on the other hand, they are both in the range between 0 and p, and therefore there is not enough room between them to have a multiple of p. Okay, so now let's say Alice and Bob are using DES, which requires 56 bits. They could say, well, we're going to use the low order 56 bits of this common key, Ka and Kb. Both of them know Ka and Kb. The eavesdropper can't calculate Ka or Kb unless the eavesdropper also knows either Xa or Xb, but the eavesdropper can't find those numbers unless he can solve the discrete logarithm problem. Okay, so this is how Alice and Bob can choose a common key over an insecure channel. Now, although this protocol provides the secure communication between Alice and whoever is at the other end of the communication line, it does not prove that Bob is at the other end of the line. So Alice has to be willing to talk to whoever is at the other end. Maybe it's Bob, or maybe it's someone impersonating Bob. So this particular protocol doesn't solve the problem of proving to each person that they are who they claim to be. Okay, well, let's talk a little bit about discrete logarithms. We have seen three different cryptographic tools. The Diffie-Hellman key exchange, the Pohlig-Hellman private key crypto system, and also mental poker. There's a few other cryptographic tools that also depend on the discrete logarithm problem. So once more, this problem is we're given a, b, and p, and we have to find x so that a to the power x is congruent to b modulo p. Well, there is a reason why these are called discrete logarithms. If a to the x is congruent to b, then in some sense, x is the logarithm to base a of p, where the modulus log to base a of b, where the modulus p is understood. Okay, discrete logarithms have many nice properties, just like regular logarithms. For example, the logarithm of a product, b times c, is equal to the sum of the two logarithms, except that because of Euler's theorem, the arithmetic with the logarithms must be done modulo p minus 1. When you add the two logarithms, if the sum is greater than or equal to p minus 1, you have to subtract off a p minus 1 to keep it in that range. Likewise, the log of b over c is the log of b minus the log of c, and so on. Okay, so now let's consider ways that we might solve this AX congruent to B modulo P. Well, there are two really naive methods that I'm going to mention here. This, you can solve this discrete logarithm problem in time, a constant times p, and constant space by raising a to the first power, second power, third power, fourth power, and so on, modulo p, and comparing each remainder with b. When you and you also keep a count of how many times you multiplied together a. So this is a to some power. And when you get a match, a to some power is congruent to b. Well, whatever the power was, that's the answer. That's the number x. Okay, so that's a really dumb way of doing it. But if you have a small enough number p, you can solve it that way. You can also solve the problem in essentially constant time. You may have a power of log p or something, but a whole lot of space. If you look up x in a pre-computed table of pairs x and a to the x modulo p, sorted by the second component. Okay, now, of course, it would take a long time to pre-compute this. You would have to perform essentially p operations, and then you would have to sort it. You have to sort p minus 1 numbers, and this would take time p times log p. So it would take quite a while to do the pre-computation. But if we choose to neglect that, then you can solve the discrete logarithm problem in constant time just by looking up the value of b in the second component. These are all sorted by the second component, so you can do a binary search to find b. Okay, now there's another method that it's a compromise between these two. One method, these are two very naive methods. One of them uses a constant times p time and constant space. The other one uses constant time, but constant times p space. There is a new method. Hey, this is even better. I like this better. I think I'll keep the white sheet on the back here. There is another algorithm. This is called Shanks giant step, baby step algorithm. This is a meet in the middle method. If you know what that is. If you don't, well then this is what a meet in the middle method is. The idea is that, well, okay, I'll get to the idea in just a second. We solve the congruence in a constant times the square root of p time and a constant times the square root of p memory in the following way. Okay, recall that we're trying to find the number x so that a to the power x is congruent to b modulo m. Modulo p. We'll let m be essentially the square root of p. To make it work perfectly, you choose m to be the ceiling of the square root of p minus 1. Some number very close to the square root of p, and maybe just a little bit bigger. Okay, now we're going to do two computations. We're going to compute the m ordered pairs j, comma, a to the m times j power remaindered modulo p, where j goes from 1 up to m minus 1. So we calculate these m ordered pairs, and we sort them by the second component. Okay. Then we also compute more ordered pairs. Call it I, b times a to the minus I power modulo p, for I goes from 0 to m minus 1. Now, of course, this has a negative power. The way you do this is you first of all compute the multiplicative inverse of a one time using the Euclidean algorithm. Once you have that done, you take that multiplicative inverse and you raise it to the power I. Okay, so you can calculate each of these iteratively by multiplying the previous one times 1 over a modulo p, and then you add 1 to I, then you write that out. Okay, and then after you calculate all that, you sort them. Okay, so how much time have we spent so far? Well, we've got m ordered pairs here and m ordered pairs here, and we also have to sort them, so they take basically m times log m. Well, we are ignoring powers of log of p, so this is basically the square root of p steps. Okay, now you look at these two lists. Look down through these two lists and try to find a pair from each list that have the same second component. Call the second component y. Okay, so you want to find a pair in the first list, a pair jy in the first list, and a pair iy from the second list. And let me explain why we should expect to find such a number. Well, there is this unknown number x. We don't know. Okay, we would like to find x. Okay, write x in radix m. M is this number here, square root of p minus 1. Write it, and since x is between 1 and p minus 1, this would be a two-digit number. That is, it is between 1 and m squared minus 1. So you can write this x as a two-digit number in radix m. Write it as the number ji. In that case, x is equal to m times j plus I. Okay, and so if you look at the number who's in the first list, which has the j in it, it'll have a to the power mj. And if you look at the number in the other list, it'll have with the I in it, it'll have b times a to the minus I modulo p for the second component. Okay, I claim that these two numbers have to be the same number, and that's because if you calculated a to the power x, you would get b. That means that if you calculated a to the power mj plus I, you would get b. Now, in that congruence, divide both sides by a to the I, or multiply by 1 over a to the I, and then on one side you get a to the mj, and this is congruent to b times a to the power minus I. So this is the number that you will find. And okay, so I'm just going to flip through the rest of the transparencies quickly. There are some faster ways that you can solve the congruence a to the x congruent to b modulo p. One of the methods is this, which I'm not really showing you, but at the end of it, you can show that you can do it basically in this time. That is, you can solve the discrete logarithm problem modulo p. You can solve a to the x congruent to b modulo p in time e raised to the power square root of log p times log p. And it turns out that is sub-exponential time. And but even so, it still takes a rather long time. There are some other methods that are slightly better than this, but this is very close to the best method. Okay. Are there any questions? No? Okay. Well, then let me stop here then. Thank you.